I achieved this approximating model for data produced by this formula, and I used my own method of symbolic regression. Great, isn't it? I thought, what is the minimal heuristic for optimization and learning? I'll skip for you my delirious chain of thoughts, and the final answer is a repeating of the successful action. You see, we humans, animals, artificial systems should notice some sort of dependency in the nature. We should map one thing or action to another thing in the future, and then we must repeat it if consequences are okay. If situation is still normal for us, we are repeating more and more. This happens when we change parameters based on the gradient descent. We do that when we prepare eggs by heating because the last try gave us cooked meal. A dog takes action assuming good and bad results of obeying or disobeying in the past. This algorithm is not the most efficient for a particular situation, but rather trustworthy in the general case. At least we don't need derivatives. Then I thought about symbolic regression. I'm impressed by Miles Cranmer's work and the Cindy model of Stephen Brunton. So assuming our findings, what if we teleport ourselves in the dimension of functions? And the real fun begins. My idea is to implement some random function on the data. If utility function is better, I keep implementing the same function further. After this procedure, we obtain the peak function describing data. This function has a view like this. I remind you, this is a result for a quadratic polynomial. It looks great, doesn't it? And this happened in 1 second, literally. But you still need several attempts for finding the best variant. In more details, if you are interested, I formed a list of functions allowed in our space of analysis. I choose simple adding, multiplying, and sine function and scaling. A list may be rather big and complex, but for our purposes, this one is sufficient. And one more thing, in multivariable world, model picks also a variable for implementing function. We can use matrix form and apply functions on all data every time, but I don't want to screw up with broadcasting issues, and we don't know exactly significant variables. In my opinion, this is more honest. Plus, we don't need huge computations at once. A loss function is replaced by utility function. In our case, it's ordinary MSE loss function, but with a positive sign. I prefer fitness or utility function because of more generality. Maybe I'll explain sometime. And now about the main algorithm. It looks like this. Model randomly generates function with the parameters, applies it on data, and computes a utility function. If utility value is higher than previous, we confirm using of the given function with the given parameters. Then we use again the same function with the same parameters, but on data changed by the previous step. It's very important. This is the core of the algorithm. We check improving of the utility function. We approve again applying of these functions with these parameters. If not, the system randomly chooses another one, and so on until we exceed the numbers of epochs. Example with the numbers. Not functions for simplicity. Our goal is 6. We have 0 now. Model gives us randomly -2. We reject. It proposes +1. We admit. We have a +1 now. Then model apply again +1. We admit. So we obtain +2. And again till we receive 6. After several experiments, I add segments for keeping flexibility. And the type of symbolic function has this view. Only one segment tends to linearization, and I would prefer to avoid this trap. After all, we can make several segments or make special system for adding segments depending on progress in utility function, etc. Now 2 is sufficient. In the beginning we train the first segment, and after the second, taking into account the first one. After all, we receive the list of applied functions with its parameters, and we can apply it on every data if we want. I mean on test data also. And voila! By the way, we need to track only several variables during computations. It's so quick. It's so perfect. But what's the trick? Some troubles with cyclic functions. It finds some cyclic features, but not perfect. Or it draws a regression style line. Maybe it's because of the very cruel rule of function allowance. We accept only the growth of utility function, but searching of optimum requires passing through areas of local diminishings. I should fix it. But model can choose different paths of symbolic search. Some of them are better than others, so we need more tries to find the best one. However, described algorithm opens the vast direction of research, and it's awesome.